For meteorologists, the laws of typhoons are ironclad. Once a monster storm hits land and is declared dissipated, it is not supposed to come back. But just hours after Fong Wong's collapse, an offshore buoy reports an impossible 8 millibar drop, pointing to a storm that refuses to die and turns back toward the battered Philippines. If the science is broken, how do you forecast what comes next? At 7 o'clock in the morning on January 10, meteorologists at Pagasa issued the official dissipation declaration for Fong Wong. The storm had crossed Luzon, battered by mountains and stripped of its core heat supply. Textbook guidance was clear. Once a typhoon's eye breaks apart over land, the energy source is gone. Within 72 hours, the circulation should unravel, leaving only scattered thunderstorms and a fading pressure pattern over the sea. This is the standard decay rule every forecaster learns, the moment when a storm's threat is supposed to end. But that morning, the duty forecaster on the night shift still watched the numbers. She later noted in the log that they expected the core to collapse. That was what the books say. Yet the surface maps refused to settle. Instead of the steady rise in pressure expected after landfall, the isobars offshore stayed tight. The models called for a gradual fill, but the instruments hinted at something holding together just beyond the coast. Land interaction science says Luzon's mountains should have shredded the circulation. The friction, the loss of ocean heat, and the injection of dry air all combined to break the storm's engine. Yet the atmosphere over the West Philippine Sea seemed restless. The official status was dissipated, but the data left the forecast floor uneasy. The next hours would force them to interrogate every reading, searching for proof that the storm was truly finished. Instead, the first hint of reversal was already building in the numbers offshore, demanding a second look before anyone could relax. At 8:20, the offshore buoy PH Buoy 07 anchored at 15.8 degrees north, 120.5 degrees east, recorded a sudden drop in sea level pressure, falling 8 millibars in just 6 hours. For any typhoon, this would be a warning sign. Along a so-called dissipation track, it was almost unthinkable. The automated alert triggered in the forecast center, drawing the attention of the on-duty analyst. She double-checked the time series, then reached for the cross-check. A Japanese cargo ship, eastbound for Manila, had logged a matching pressure fall and rising winds at nearly the same coordinates. The buoy's barometer had passed its last calibration 2 months earlier, and the signal was clean. No sensor glitches, no venting issues, just a sharp, coherent drop. Normally, after landfall, pressure should climb as the storm's core fills with dry air and the circulation unwinds. Instead, the numbers pointed to deepening, not decay. The analyst pulled up the pressure and intensity tables. An 8 millibar drop in 6 hours corresponded to a rapid reorganization, the kind seen only during explosive intensification phases. The models had forecast a gentle rise, but now the instruments were telling a different story entirely. Independent confirmation from the ship erased any doubt. This was not an instrument error. The storm's engine was rebuilding offshore, defying every textbook rule. With the local radar network still degraded from the first strike, attention turned to the only remaining eyes in the sky, satellite feeds, hoping for answers that the surface network could no longer provide. Himawari 9's infrared feed began rolling in every 10 minutes, each frame a fresh test of the forecast. At 10:50 UTC, a scientist at the JMA satellite desk watched as the storm's core, thought to be fading, flashed a new signal, a dense cluster of cloud tops with temperatures plunging to minus 70 degrees Celsius. That number is not just a statistic. Minus 70 means convective towers have punched into the lower stratosphere, a sign of explosive thunderstorm growth. For a typhoon supposedly in its death throes, this is the satellite equivalent of a flatline spiking back to life. The infrared loop from 10:30 to 12:30 UTC showed the cold shield expanding, wrapping tightly around a circulation that should have been unraveling. Instead of the ragged, warming cloud field expected from a dying storm, the images revealed symmetry and intensity. The Himawari scientist logged the anomaly, noting that only a handful of storms ever display such cold cores after landfall and almost never on a dissipation track. The satellite data validated the offshore pressure drop, confirming that Fung-wong's engine was rebuilding offshore, ready to defy every rule in the book. Sea surface temperatures in the West Philippine Sea stood at 1.4 degrees Celsius above the late-season average. It was enough to supply vast reserves of latent heat to any passing cyclone. Ocean heat content profiles showed a deep reservoir of warm water extending well below the surface. According to Dr. Rafael Cruz, a regional oceanographer, this combination meant the ocean could withstand even the strongest churning from typhoon winds without cooling off. That deep warmth served as an open fuel tank ready to power renewed convection. At the same time, vertical wind shear dropped from near 10 knots to just 6, removing one of the last atmospheric barriers to storm organization. In typical post-landfall setups, strong shear would tilt and disrupt any attempt at core rebuilding. Here, the atmosphere offered little resistance. Overlaying all of this, the Madden-Julian Oscillation entered an active phase directly over the region, pumping extra moisture and upward motion into the air column. Every major ingredient for rapid intensification, warm water, deep heat, minimal shear, and a primed atmosphere came together at the precise moment Fung-wong's remnants hovered offshore. The physical environment was no longer hostile. It was primed for a comeback. Inside the National Forecast Center, the network operations chief scanned the status board. Red and yellow icons marked where the system had gone dark. Legazpi's Doppler Radar, critical for monitoring Bicol and the southern Luzon coast, was offline after its power feed failed during the first landfall. The main tide gauge in northern Samar, used to track coastal flooding, had stopped transmitting hours earlier. The last signal was 3:12 local time. Across the region, more than half the surface weather stations were down, either from wind damage or lost communications. By midday, only about a third of the normal real-time observation network remained. The chief's phone buzzed with requests for updates from field offices. With so many instruments out, the team relied on patchy satellite data and a handful of surviving buoys. Every forecast now carried a warning: confidence low, visibility partial. Decisions about warnings and evacuations had to be made with just fragments of the picture. For scientists trained to trust the numbers, this was the nightmare. They were tracking a storm that refused to follow the rules, with the tools meant to keep people safe already crippled. In Verac, the municipal disaster officer stared at the shelter lists. Every classroom, chapel, and gym was already full. Over 1.3 million people had evacuated before the first landfall. Nearly 500,000 people remained displaced, their homes ruined or unreachable. Now, with warnings of a second strike, the numbers no longer added up. Emergency stockpiles were stretched thin, and some barangays had no safe route left. Bridges were out, and roads were blocked by landslides. Families who had spent days on concrete floors hesitated to move again, fearing for what little they had left behind. The officer's phone buzzed with calls from village leaders asking for transport, for food, for answers. With shelters overflowing and uncertainty growing, every decision carried the weight of lives at risk. Dr. Liza Ramos runs the latest compound flooding models for Albay and Catanduanes. Her simulations show storm surge pushing over seawalls already cracked by the first landfall, and flooding low-lying barangays that had barely started to drain. In river basins, the soil remains saturated from days of previous rain, and now with new rainfall piling on, the rivers have nowhere to send the water. The models predict a surge front colliding with swollen rivers, sending floodwaters deep into towns that escaped the first wave. On the slopes above, landslide risk triples. Dr. Ramos points to debris flow projections, showing entire hillsides primed to collapse. For communities below, the threat is not just water, but walls of mud and rock moving faster than anyone can outrun. The numbers leave little room for hope. Every weak point from the first strike is now a target. Dr. Marissa Tan sits at the center of the National Ensemble modeling team, watching the latest forecast runs widen across the screen. In the IB-Trax archive, cases like this, where a typhoon reverses course and re-strengthens within 72 hours of landfall, account for fewer than 2% of all storms that have ever struck the Philippines. The models now scatter wildly, some tracks looping back toward Luzon, others dissolving over open water. Dr. Tan's team debates which scenario to trust, but the spread itself is the warning. The system is operating at the edge of what history and physics can explain. She recommends urgent deployment of mobile sensors and rapid response buoys, knowing that standard networks were never designed for events this rare. For scientists, this is not just a forecast problem. It is a signal that the climate system is writing new rules faster than the models can keep up. Today's storms rewrite the rules faster than science can keep up. As oceans warm and extreme events multiply, certainty vanishes, while risk keeps rising. When nature breaks the models, millions wait in the gap. The next storm may not just surprise us, it may outpace what we know.